Okay, hey everyone. I'm Karun. I'm one of the devs here at Sahaj. So yeah, the slides, if you're curious, there's a link to the slides at the end. So in case you're missing something, you don't have to frantically take notes. You will get the slides. I'll put it on the meetup as well. And there's a Twitter handle in case you want to get in touch and you have questions later. Feel free to drop me a DM. I'd be happy to sort of start a conversation there. Okay? Okay, cool. So let's do take 2. Hi, my name is Karun, and I'm a developer at Sahaj Software. So today we're going to be talking about machine learning to detect fraud. But first, let's sort of understand our client story, right? So a couple of years ago, one of the clients I was working with wanted to sort of launch a new product to the market. They're a financial client who's been primarily working in North America. They wanted to sort of launch a new product and they required a platform to do so. So the first thing they asked us to do is to come in and help them build a sort of a platform for them to launch this brand new product, in this case consumer loans, but then extend it so that they could also do other kinds of products. So as the sort of platform, like once the platform stabilized, we obviously started ramping down. So then the client actually came back to us and said, hey, there's another challenge that we would like you to sort of come in and help us fix. That was essentially fraud detection. So since they are sort of a financial firm, they're primarily dealing with credit applications, right? Like credit cards, consumer loans. And fraud's like a pretty big challenge there. So the way financial institutions actually deal with fraud is that they keep a budget aside, generally, that they're essentially willing to leave, like sort of write off. So here's X amount of money I am okay losing, and as long as I'm below that, that's fine, right? And if that X is big enough, that's obviously a problem because it's a cut on your bottom line. It's money that you're losing. So they came in and said, we're feeling a bit unhappy about the amount of money we're losing, but we don't know what else to do, right? So let's try to understand what credit card fraud looks like. Try to understand the domain, because then the solution hopefully makes a bit more sense, right? So in credit cards, there are 3 primary types of fraud. The first one is the obvious one you can probably think of, transaction fraud. And what that means is, if your card gets stolen, what's the first thing somebody would do? They'd go to a store, show up there, and start racking up money, right? Start shopping for that big TV that they want, a new sofa, or whatever else, right? So as long as the card doesn't get blocked, great. Like they'll keep trying to rack up money. So the loss is pretty direct there because most customers on these credit cards will have insurance, and the insurance will take care of it, but the company still has to take a bit of a loss. So the insurance doesn't cover all of it. From a customer standpoint, they're fine. From a company standpoint, they're not because they do lose money on it. The second kind of fraud is application fraud. And what application fraud means is it's essentially an attack of kind of like identity theft, right? So I'm going to pretend to be you. You have a good credit score. I'm going to take your name, your social security number, and pretend to be you and apply for a card, except the card will come to me. Guess what happens now? I have a credit card which you have to foot the bill for, but I get to charge money on it, right? So the simple version of this is the month I get it, I rack up all, like, again, go on a shopping spree, take as much money out as I can, and you're left with the bill. And even if you're not left with the bill, at the very least, you're left with a bad credit score. And usually this takes years for someone to fix. So it's pretty malicious. I hope, and this is a pretty major problem in sort of the North American market. The third kind of fraud is card not found. Not to be confused with 404. This is as simple as you can think. Like if your card is being mailed to you, all that person has to do is go to your mailbox, take the card out, and be like, hey, I found a card. Guess what? Now I can go and spend money. This also happens to be the easiest one to tackle, and companies have this tackled pretty much. What they do is the card's not activated. So if you've received a debit card over the past couple of years, remember you have to pick up the phone and probably call in and say, can I enable this card, or go to the web portal and do it. This is the reason why. So essentially a man-in-the-middle attack can be stopped. No one can steal money from the bank until it's been validated by the end customer, right? So that's why they have that auth check. So out of the 3 types of fraud, the one that we sort of first focused on was application fraud. And there's a simple reason for that. Because when you want to sort of set up an MVP, the thing that you want to pick up is the kind of product you want to work on is something which does not have stringent requirements in terms of performance, something which can very quickly be validated, or at least, it's not as hard to do. So between the three, the third one wasn't as much of a problem. Transaction fraud, the challenge is that you have to essentially run your model every time there's a credit card swipe, right? And you guys are used to swipes, so you know it takes like a second to a second and a half for the entire process to happen. The bank gets 10 milliseconds to respond to a request for fraud checks, right? So in that 10 milliseconds, you're supposed to get the request, process it, tell them whether you want to allow this transaction or not. Not looking at how much balance you have left and all of that, just from a fraud perspective, given whatever data you have, do you think you should allow this or not, right? So in terms of performance, it's really, really hard to sort of get this right. So that is probably not the MVP that you want. With something like a credit card application, the person's waiting there for a couple of seconds. So it's a lot easier to do this, right? So we said, fine, let's do application fraud first, and then build a framework which makes it easier for us to also tackle other kinds of fraud. Right? So the solution that you'll hear is a lot more generic, but it was first used for application fraud. Okay, so let's first try to understand what was the system in place before we jump into our solution. So when a customer is sitting at home and they want to apply for a credit card, the most common way in North America is to go to a website and say, I want to buy a credit card. I want to apply for a credit card, right? So when you do that, you fill up an application on the website and you call a request. You send a request. The request goes to a service. Now the service does is that it does a bunch of validations, goes through the rules that the bank has, make sure the data is appropriate. But after that, when it comes to the fraud bit, which is what we're more interested in this case, the bank happened to sort of outsource that call because initially they didn't have the expertise to do this. So they had a vendor who would specifically handle the fraud detection for them. And the way they did that was in 3 steps, right? Rules, models, and strategies. So we'll talk about this in a second. But when the request went, the time limit that they had, this system would actually respond in the necessary sort of performance window. It will send back a score. Now, once it gets the score back, the service decides whether it wants to go forward or not, and then returns the response to the customer. Right? Pretty straightforward. Most of the processing happens in the center, inside the bank, between the 2 lines, and the stuff on the right-hand side is outside the bank's network. Right? So let's look at what the vendor actually does. Right? The rules, models, and strategies. Step 1, rules get executed. So rules are essentially what you can think of in terms of like typical rules engines. Right? So somebody's gone in, set up a bunch of rules to say if this happens, this is what the response should be. I'll give you an example. If let's say holiday weekend, they start noticing they're getting a lot of spam applications with a certain domain. This actually does happen, right? So they will actually go in and blacklist those. If they see there is a big data leak and a bunch of SSNs have been compromised, there is a very high likelihood that those, like any application which comes immediately after, is actually going to be from people who are sort of trying to commit fraud. So they will put in rules to essentially make sure that these get caught because as you were mentioning earlier, the model has not had enough time to learn and become better, right? The thing with machine learning models is you have to train them. For training them, you need data. To have data, you need to unfortunately, a few frauds will have to go through before you learn that it's actually happened, right? But if you know there's a high likelihood of there being fraud from a certain area, why give up that money, right? So there has to be some safety net to make sure it works. So the rules are the ones which take care of that, right? Where I am making a decision as an admin that this is what I need to do. Don't even run the models, just listen to me, this is fraud, right? So those are the rules. The model is the primary bit that we are focusing on. It's essentially a trained model that the vendor had, which was trying to classify something as fraud versus not. And so when I say fraud versus not, well, actually, technically, the model actually returns a score between 0 and 1. It doesn't actually say whether something's fraud or not. The strategy is the bit which actually defines what is considered as fraud. So what I mean is, score is between a big range. Strategy is essentially a rule to as to what to do with the scores. right? So if your fraud score is too high, let's say 0.8 or above, then it's definitely fraud. Don't even look at it. Because banks don't directly reject applications. What they do is, most often they will pend the application. So there's accept and reject, which is what we generally think of. And then there's the middle, which is you are in pended state. We are manually reviewing the application. So if you're sure that you're a good customer, we will take you in. If you're sure you're a bad customer, we'll reject you. But more often than not, you're somewhere in the middle and a human being needs to look at it. And the reason why this area exists is the models and the rules, they help the human being make that decision. As to how likely we think it is fraud, that we'll spend more time validating that the customer is real when we think the model sort of outputs that this is probably a high likelihood of fraud. So the strategy essentially is sort of what is the reaction or what the bank wants to do with this information. So now that we've sort of looked at what the current state looks like, let's look at what we are actually tweaking, right? The overall business process doesn't change as much, but we are essentially in this sort of migration process, we are trying to phase out individual parts. We're trying to reduce our dependency on the vendor, primarily because the vendor, in this case, happened to take 36 months to actually make a change. So you go and decide one coefficient needs to change on anything, right, except the rules. The rules has like an admin UI, you can go and change immediately, but the model or the strategy, if anything has to change, however small it is, there's a 36-month release process, which is unfortunate because you can't react quick enough, right, and which is one of the reasons why we were asked to come in and help. So here's what we proposed as a solution, right? So, so what we've added is a bunch of challenger models. So the data scientists in-house are going to build models. They're going to experiment, essentially say, I think this might be better, I don't know, we have to test it, right? So we call those challenger models. And so what we do is when, so these are still theory, these are still, it's still a hypothesis. We are not sure whether it's actually better or not. So what we're going to do is, we're going to like call as always, but when we send the call out to the vendor, we will also send it to the challenger models. All of them will run, they will produce some sort of output, and we will store it somewhere. What this allows us is that when we have the response back from the actual system, we can do a comparison, right? And then we can look at it retrospectively to see, when are we better than the model that the vendor has? Because in a financial institution, the risk is quite high because the amount involved is very high. They don't want to make a change until they are confident that something works and something's actually better. So we're going to send it in, we're going to look at the data, we're going to prove that the newer system is more effective, and only then will we make only then will they approve a change to be made in production, right? So all of this is fine, but once this validation actually goes through, what do we do next? We have to actually make a change to production, right? Because so far testing the model does not actually give me value. So we'll promote one of these to what we call as the champion model. It means it's the one that we've chosen, we think is better, we have data to prove it. And so once we're ready, we'll do the same thing again. Once an application comes in, the call will go out to execute the rules because we don't have the rules, we're just building a model. The response comes back from the rules, and if appropriate, if the model needs to be executed, now the request goes to both systems. The challenger models execute in the background as always, but the champion model actually gives me the output, right? It's the one which makes the decision. But the output of the model is a score, right, between 0 and 1. So what do you do with this score? You still have to send it back to the strategy. You still have to execute the strategy, which actually explains what the decision is. So when the strategy says yes, go ahead with the customer, or no, just reject the customer, we listen to that. And once this call is complete, we will sort of give the decision back to the user, right? So this is what sort of the overall process looks like. This is, as I said, like this is just one part of the system that we are taking out. There were 2 other projects to get the rules out of their systems, of the vendor system, and get it in-house. And there's also a strategy piece. Both of these have their own complications because there's a lot of workflow involved, especially in the strategies bit. So those were 2 completely independent projects. But all 3 of them essentially worked on the same interface. So we could run all 3 projects at the same time. Okay? But the one we are going to be focusing on primarily is the models bit. But if you're interested in anything else, please feel free to ask me after this and we can have a discussion on that. Okay, so I've been talking about like the model and the score that it returns. Let's try to visualize that to be able to understand what the model is actually giving and what it means. right? So if I were to plot sort of the model score on the x-axis against the number of applications we see, what you would notice is for applications which are not fraud, you'd see a curve which is more heavier towards the left, right? So lower scores are have a lower probability of, essentially this is a probability between 0 and 1, so lower probability of it being fraud. There's another curve, if you draw sort of the fraud curve, you'll notice it's higher on the right hand side, right? But the interesting thing to note is that there is an overlap, right? So there's this huge area at the bottom where we think like it could be either. So how do you decide what is considered fraud versus not, right? So you've got a threshold at some point. You've got to choose draw a line somewhere. In this case, I've drawn it at 0.5, but it really could be at any place. You draw a line at some place, and then you decide anything to the right of this, I don't care what the score is, it is going to be considered as fraud. Anything to the left, it is considered as not fraud. Now, what happens as a result is there's this huge area here of customers who were not non-fraudulent. They were legitimate customers, but unfortunately we classified them as fraud, right? These are called false positives. On the other side, you have a bunch of folks who were actually fraudulent, but we let their application through. No model is perfect, right? If you had a perfect model, you'd see a box on this side drop to 0 and then another box on the other side, right? And you'd have a clear distinction between the two. But in real life, you never have that. You have overlaps, and so you end up losing money either way, right? Because any false positives means that's good customers you could have had, and you have customers because, well, if it's a bank, the bank makes money off of customers, right? So every customer you lose, you're losing some money. Every fraudulent customer you're letting in, you're losing money, right? So how do you figure out what the sweet spot is? Like, because I just drew the line arbitrarily at 0.5 because it's easier to visualize. But how do I understand what's an appropriate place to draw the line? Well, that comes through a formula called the loss profitability formula. So what we're doing is we're calculating loss profitability as sort of a product of the cost of fraud. Every time fraud occurs, how much money do we lose? And multiplying it by the number of folks that we are letting through, and then adding to that the amount of money we lose because we lost a legitimate customer, right? And there are versions of this that you will have in your own application whenever you're trying to do this, but essentially you're trying to minimize the function for loss profitability, right? So draw the threshold at the point where loss profitability is minimum because you're losing minimum amount of money. And for this, you need to have these two variables, the opportunity cost as well as the fraud cost. And if you're a data-driven organization, that's a bit easier. If you're not, then unfortunately you have to get that information because you have to know how to be able to optimize these curves, you have to know the values of these things. Well, it was a bank, so they know how much money they lose overall per year, how many people they let through, so they divide the two and get this information. It's not too hard for them. Okay, so now we're going to be talking about sort of the model training process. So what we're doing is called as supervised training, which means we seem to have information, we have information which clearly denotes what is the answer, because when an application is marked as fraud, there is data that the bank has collected over the multiple decades that it's operated. It is tagged it clearly saying here's where we lost money, this was fraudulent, here's where we think it is not fraud, right? And that's also an interesting distinction that we'll talk about later, because you're never sure something's not fraud, because people apparently get credit cards, pay their bills for years before they commit fraud, even though it's a fraudulent application, long-term play. But anyway, so when you get this data set, you take this information and actually you try training it. So the way it works is you get the historical data, you run it through some sort of model, and the model is really dependent on the problem that you're trying to solve and what works best. Once you have this, it is going to output something, and the output is going to be given a single input. It is going to tell you yay or nay, like whether something's whether an application is fraudulent or not, right? In terms of the score that we were talking about earlier. But that's what it's going to be attempting to do, right? For us to be able to do this, we need to have information. We need to have data, because without data, we cannot train a model. So let's talk about like what are some of the patterns that and no data that you get is going to be perfect. So we had to essentially develop features to make the model better. So we'll go through some of the techniques that we use to clean, to massage the data, to make it better, and some cases where, a couple of examples of where we've created features which help us predict fraud better. So the patterns that we used are essentially filter, transform, impute, and developing features, right? Feature engineering. Let's go through them one by one with examples to help you visualize what that means. So when you get data, so in this bank, by the way, when we get the raw information, the whole dump of information, there are 276 columns, which like data points, and the 277th one is happen to be fraud versus not fraud, the answer, right? So 276 data points based on which we have to decide what is considered fraud versus not. We don't know which ones are important. We don't know which ones are super important, right? So we don't know which features to select. So you have to take some effort to reduce this set, because otherwise your model will take too long to train, or your model won't be accurate at all. Some of the techniques we use to be able to do this are looking at the cardinality of the data. So for example, there happens to be a column which is primarily completely going to be, the application type is going to be credit. As I said, like the product that they launched, they've been in market for like over 20 years. They were giving out credit cards of different types, but credit cards nonetheless. And then recently they started credit loans as well, right? So there's some loan information in there, but almost always it's credit card information. And we're trying to catch fraud only for credit card. So when you filter the table out and look at the information, this column is actually worthless to you, because everything's going to be a credit application. There is no correlation between the application type and your fraud status, right? So anything which has very, very low cardinality, you probably want to drop. Especially if the cardinality is 1. The next thing you want to look at is something which has very high cardinality, and a great example of this is name, right? There's almost no bearing of the name and whether you've committed fraud or not, unless you happen to be a known fraudster, in which case there's probably a rule about your name to pull your applications out. But yes, so like looking at this information doesn't give you too much information. I can't really come out with a pattern to say all Johns seem, I can't look at this data point and say all Johns seem to be fraudulent. Like that's a bad implication, right? So this information is not too useful. The kind of information you want to look at probably is something which has medium cardinality, right? Only a handful of unique values in a column. So submission method is a good example of this, right? So if you look at this, well, in this sample set that we've created, it seems like it is quite probable that there's a correlation between the type, like if it's web, then there's a good chance that it is fraudulent. That's not actually true, but just to make a data set, like you can come up with inferences like that. So this makes model training better. Another example of data, another thing that you do is data transformation, because the data that you get isn't always something that you want to use, but you can make it better, right? So an example of high cardinality is email addresses, because you will almost always have unique values when it comes to email addresses, unless someone's applying again and again, or someone's using someone else's email, which is just weird. But what you could do potentially is drop the email, the first part, which is the username, and then focus on the domain name, and then certain patterns emerge. And in this example, we've obviously used fraudster.com, which makes it easier to spot these things. And also you might be thinking that this doesn't actually happen, but turns out there are certain domains out of which there is a higher chance of it being fraud, because they just happen to use those because the verification required and sort of the data tracking policies and stuff are lesser there. So people tend to use that, and plus there's APIs available to programmatically do stuff. So you'd see lesser maybe Gmails because there's a CAPTCHA and good CAPTCHA, as opposed to some small email server which has almost no restrictions, and you can programmatically just create as many emails as you want. So those things end up actually helping when you want to sort of filter information out. The third kind of thing you do is imputation, right? Because data isn't always available, either because we've lost data, we've not recorded it correctly, or just it wasn't a mandatory field in the application, right? So an example of this is, has someone applied before or not, right? Either because you already have a card and you want a second card, or you've applied and it's been rejected in the past and now you want to apply again, right? But sometimes you don't have a value. So what do? You have to come up with a default value because you can't train on null values. So if it's like a Boolean value, think of a default like false versus true, but be very careful when you select a default, because it has a huge implication on how you train your model, right? Because you're skewing the overall, so if you are used to visualizing something as a histogram, the distribution is now changing and the model actually gets trained on the distribution. So what I mean by that is, it looks at the information in a column and it will make inferences. For example, for applied before, let's take false as an example. For salary, let's take average as an example, right? So it might be making like buckets to say anyone who's between this salary range, there's a high likelihood that there is fraud. But because you now added default values, that distribution changes and the decision making changes. So the question is, do you want to use like a default value based on just doing an average of the people who've applied, or do you want to do an average based on the national census? Because in countries like US, and I'm guessing in other countries as well, there is census data provided. So per city, you can actually check what the average salary is, right? You could do that based on profession as well. You could drill that down, right? So you could have smarter defaults, but defaults nonetheless. The question is, which one works better? You have to experiment with the data to find out what works better. So yeah, something like this, this also helps. So next, let's come to feature selection or feature engineering. So here, what we're going to be talking about is like you have data available which seemingly seems not as useful, but out of that you can create a feature which is more useful. For example, zip codes, right? A classic case of having very high cardinality because the number of zip codes in a country is pretty large. So that's not going to be super useful. IP address is usually recorded when you do an online submission. That's also pretty much unique, not super useful. But one of the things you can do is realize that both of these in some way or form represent location, right? This is the location of where you live because I asked for the user's address. This is the location of where you applied from. And if you think about it, there is a correlation between those two. You're probably going to be close, like when you apply for a card, you're probably going to be close to where you live, right? Either you're going to do it at home or you're going to do it at work, and most people work close enough. So if you start calculating the proximity between these two locations, you might end up realizing that there are trends. If if the zip code is from Chicago and the IP address is from Sydney, pretty high chance that someone's sitting halfway around the world and applying. So one of two things has happened: either the person's on vacation, or the person is not legitimate. Turns out when we did sort of an analysis on the data, there are very few people who were legitimate users whose location was like the proximity number was too high, and still they were legitimate because there are very few people who travel that far or even on vacation think about applying for a credit card, right? But this is a good example of feature engineering, and for you to be able to do this, you need to understand the data that you have and then sort of apply some lateral thinking to think both of them happen to point towards addresses, and I can think of a correlation. But there's other techniques to figure out, like sort of analyze your data and figure out correlation as well. Okay, so now that we've talked about sort of how the data was processed, how the model was trained, by the way, we used random forest as the algorithm of choice because we were doing binary classification. I apologize, I forgot to mention that. Okay, so now we're going to move towards sort of more of the application side because we want to talk about what is the workflow, and there are two unique workflows from a development perspective on the team, right? And what do these two workflows look like? So if you're a data scientist, what you're looking for in a system is slightly different. When you're a developer, what you're looking for in a system is slightly different. Both happen to be important for their own reasons because both of them are essentially trying to build features in the product to get to market quicker and essentially come to the same goal, which is save the business some money. So let's talk about sort of the data scientist flow first. At a high level, you go from raw data, you transform it, you massage it, and then you eventually come to a trained model, right? Though that's the responsibility. And what the developer is ending up doing is continuing from here. Given a trained model, they are trying to build an application which can be put into production because it has to respond to requests real time and answer whether an application is fraud or not, right? It's not being done in batch. We don't respond at the end of the day. When the customer is sitting there clicking on the button for apply, we have to give an answer. Or if it's transaction fraud, the same thing. If you're at the POS and you swipe, I have to give you an answer. So somebody has to take that model and actually put it to production and make sure it responds within the necessary time limits. So let's sort of expand on both of these areas to try to understand a bit more how this process actually works, right? So if you're a data scientist, what you're doing is you're taking all of the historical data that you had. You are going to take the techniques that we talked about, cleaning, transforming, and imputation, which is like using default values. In this case, what we were doing was the data scientists were using Python to be able to do this. Now, why Python? Because they're used to it, right? There were some data scientists who were used to R, right? But we decided that's a day 2 feature because almost all of the data scientists in the organization who used R were also comfortable with Python. It was just their secondary language. So we said, let's go to Python first and then sort of support R later. Build it with Python. Our framework of choice was H2O. And I know if there are folks who've worked in this field, you're probably used to scikit-learn a bit more. We had a long debate about this. The reason why we ended up with H2O over scikit-learn is H2O has this unique capability where you're essentially configuring the model or defining the model in Python, but the output is not actually Python. The output happens to be Java. It's quite contentious, but it's either a Java class or a class file, whatever you want. And the reason why specifically we had to do this was organizational rules. It's a bank, they have certain stacks, they're more used to it, more comfortable, and app devs didn't feel comfortable using Python. Also, if you put a new language into production in a bank, you have to talk about the full stack. How do you build it, monitor it, maintain it, right? In the long term, you have to talk about all of those, which takes the overall cost of ownership of a product higher. So we say, fine. The two sets of folks who work on this product have 2 different skill sets, and we will support both of them. So H2O does the nice job the hard job of converting between the two, and it produces a class file. We take the class file, automatically compile it, give a jar, and that jar gets pushed into an artifact repository because every build of a model is essentially an artifact. If you're from the Java world, you think of jars. I mean, this happens to be a jar, I know, but the model is essentially a versioned artifact now, right? And there's tests and everything run on this. So the next thing we're going to be looking at, so you've gone essentially from raw data to transform model. So that's the sort of input-output of the entire developer workflow. The next thing we're going to be looking at is what happens with the developer workflow as soon as this transition completes. But the developer workflow, what we're going to do is we're going to start exactly where this ended. The developer is going to start on their own workstation, and like every other typical sort of software development lifecycle, you're going to pick up the artifact, the jar file from the repo, build an application around it, and have tests and everything else and deploy it. Couple of nuances to sort of remember here is that when the binary artifact gives you the jar, what you have to know is when the model was trained and that this was done in Python, the data scientists obviously validated what their score was, right? How effective they think the model was. So one of the things we did was the build process remembers that as an artifact. So you have a benchmark score. And one of the things we were asked to prove was, once you build this application, can you prove to me that the score is not changed? Because if the score has changed, it means that what the data scientist is building is different from what you're putting on production, which is a problem, right? So essentially we take that model, we happen to sort of package it using an automated process. We use a framework called Spark Java, kind of like Spring Boot, but a hell of a lot lighter, a lot quicker to develop on. And we automated this entire process. So the developer doesn't actually have to go in every time a model version gets bumped up. They don't have to go in and do anything. There's just a config file change. Say that you want to deploy with the newest version, and it will automatically deploy. So once you've done that, what ends up happening is that when the customer actually makes an application, applies an application, and so the application service actually sends us a call. We take this call. Now the thing is that when you did the training, remember you added defaults and you did a bunch of other data transformations. The data that you were using for training is actually historical data of customers applying. So if something was missing then in that data, it's going to be missing today when the customer applies. And so the thing that you have to remember is you have to do the same set of transformations you did during training again when your application is running in prod. which is why we built this sort of layer in between, which is built in Python. And the way it's built is whatever code was used to sort of clean up the data and massage the data gets automatically packaged as part of the build process and gets dumped into this thing, except it's now a web service. So when the call comes to the web service, it's going to do the same set of data transformations so that data is essentially at parity, otherwise your model score won't make sense. It dumps the data on, it dumps the request onto a message queue because these models aren't super important because they're essentially in shadow mode, right? Because when you're training the model, it's not, the response time is not important. So you're going to put it on a message queue so that the system doesn't get, the performance of the system doesn't get affected. And when the platform gets the response, it's going to dump it into a repository off of which you can build UIs and you can do all kinds of fancy stuff on it, right? So you can essentially pull reports to see how effective a model is. Now, what you're going to change after this, once the transition happens, is when something is actually put live, promoted to prod, all you change is you go from, so when you're ready, you take the model out of the vendor. Like once you've decided there's a model which is worth promoting, you will take it out of sort of the vendor. You will promote one of these models to champion mode. You will do the same thing this time, except when the rules gets called, you get the response, and the platform will make a direct synchronous call this time to the model, as opposed to the asynchronous call to everything in shadow mode, right? You see the difference why? Because everything which is like actually making a decision needs to be synchronous. You need to get a response almost immediately, and if you don't get a response, that's a problem which needs to be reported to the UI, right? So the champion mode model always gets run in sync, and everything in shadow, it's okay. I don't care if you fail if you're in shadow mode, because the failure will also get recorded and it's in a safe sandbox. So what this allows is, if you as a data scientist have built a model and it's less than perfect, the fear that usually financial organizations have is failing in prod. But now you've given them a sandbox where they can experiment and they can feel safe. So what this allows the organization is to put models out really, really quickly. And if the effectiveness score is low or the failure rate is high, it's okay. You will just kill the model when you're not ready, right? But you gather that stat, you gather feedback really, really quickly. And this becomes important for you to be able to iterate very quickly. Because remember, the problem that we're actually trying to solve is reduce fraud overall. But the primary reason they couldn't do that with the existing stack is because the vendor took 3 years to respond, 36 months to, which is 3 years. 3 years to respond to every single one of your requests. So by making this a lot quicker, you sort of move the ball a fair bit. Okay. Yeah, so once you get the response, you're going to go store it in the database like we talked about. And so the scores all lie in here. So you've got sort of your end-to-end from a customer applying all the way to you getting a score. Like you've talked about what the workflow is like. And so the last thing that we want to talk about is sort of the value stream, right? And value stream is a phrase that we use to sort of explain what the overall value is for the end customer to use this platform. Like, why do we have this, right? How do you go from an idea being thought of all the way to getting what you want? So in this case, make sure you have all of your information. You ingest the data, you clean it up, you massage it as a data scientist. So all the circular dots that you see which have an S are stages that the data scientist is working on. They will work on a model, they will train it. Once the model gets trained, here's something that we didn't talk about earlier, there's governance. If you work at a financial institution, there are lawyers who have to double check what you've done for legal reasons. An example for why you have to do this is redlining, if you've ever heard of this phrase. What happened in the 70s was someone looked at data, looked at loan repayment rates, and then found out that certain neighborhoods, if you lived in a certain neighborhood, there's a very high chance that you can't pay off your loan, right? And anyone who is in certain neighborhoods, very good chance, right? I mean, rudimentary form of doing doing machine learning, except it wasn't a machine, it was a human being doing it. The data was on point. They weren't wrong. If you lived in that neighborhood, you couldn't pay your loan off. But what they failed to understand was the reason behind why this happened. You can look this up. It's a very famous case which went all the way to court. The reason why you couldn't pay is because of the sort of the background of the people who lived there, right? So the neighborhoods were predominantly African American heritage, which is predominantly, especially at the time, was a subsection of your population which did not have as much like ability to always like pay off your loans at the same time. So what they ended up doing was, because they noticed that you couldn't pay your loan off, the risk is higher, and therefore they charged you a higher interest rate, which actually makes it worse and makes it harder for you to pay it off. Guess what? Now you made a feedback cycle, right? Like because of hundreds of years of operation, you can't pay off the loan, but now you made sure they will never be able to pay off a loan, so this statistic will never improve, purely because you've taken something like this into picture. And the reason it's called redlining is because somebody took a map, literally drew a red line saying this is the area you don't give loans or higher interest loans, and this is where you don't. So there was a law passed, you can't do this anymore, and which is why the governance process, this amongst many other rules, is the reason why governance exists. This is the reason why you can't just take a model in a financial institution, put it to prod. So that's what governance is trying to do. It's essentially trying to make sure you're not discriminating, not willfully, but like in this case, no one wanted to willfully discriminate, but they were, because they didn't realize the implication of their data. So governance is super important. But once governance says, yep, the governance process starts, you submit a bunch of documentation, which is what, like while model training and stuff, I talked about some of the things which get outputted. There are other curves, there are other statistics that get evaluated, which the data scientist looks at, and that's essentially proof of work. So they're going to submit all of that to the governance team, and they are going to review it. While the review is happening, we already published the model. We publish it into an artifact repository, and when we feel confident, we will go ahead and actually publish the service as well, which is just bump up the version, compile and deploy. The reason we are allowed to do this, and we had a huge fight about this as well, the reason we were allowed to do this was because nothing actually affected the customer. That's the bar. As long as you don't touch the customer, you can't accidentally discriminate if you're never actually making a decision, right? So the limitation was no longer deploying to prod. The limitation is actually promoting something to champion model, right? So yeah, service gets published, automated pipeline goes all the way to shadow mode. From shadow mode, you are going to start collecting results. Once you have enough information, and the animation decides to catch up with me, governance will actually look at the information for a couple of weeks, months, whatever time they seem necessary. Generally tends to be 4 to 12 weeks is what they wanted information on. They will do an evaluation based on what you suggested in the beginning and the actual data that you see. Once you do both of these, and they say, yep, this looks good, you can take this all the way to prod, you'll only go back to them and say, if you realize your model is not good enough, you're obviously going to stop the process. You're going to iterate, you're going to improve, and you're going to do this again. But eventually, when you feel confident and you get the go ahead, promote it to prod, right? And that's sort of the whole value stream. So if you notice, what we've ended up doing is a couple of things. Generally, we talk about data science in isolation. We talk about how are we going to build a better model to get an answer better. But the other side of it, which we should also be talking about, is how do you make this happen efficiently? Because if you talk about sort of the DevOps revolution over the past decade and a half, it's primarily been using engineering practices to make something happen quicker, increase those reduce the feedback time to essentially iterate quicker and get a product out quicker by essentially separating things which affect the customer versus not. And by sort of using continuous delivery practices that we take for granted, it moves sort of the whole feedback cycle, reduces the whole feedback cycle for the customer. And by automating all of this, it certainly makes everyone's life a lot better. Okay, I think that's all I have for today. I am happy to take any questions that you might have.
What is the dataset size?
Dataset size was 20 to 25 years. At this point, it's probably 25 years or so of applications leading up to, it's not that large, so it's around 22 gigabytes or so. It's not terribly large across every. Sorry? Oh, number of records? I don't have a number off the top of my head. And even if I did, I don't think they will let me mention that because that is information as to how much cards you sell and stuff. Training one model. Let's start with Okay, I think I can answer that in a couple of ways based on how I interpret the question. One of them is, as a data scientist, given an idea, if I click the button, how long does it take to build a model, right? Once we effectively did feature engineering, the model training took 104 seconds. Random forest, not too far, doesn't take too much time. We spent way longer on deciding what features to use. Because as I said, 276 columns, right? We ended up training with, I think it was anywhere between 45 to 56 based on the model that we were using, because we had multiple versions of the random forest model that we had, all with different effectiveness. So deciding what those features are took longer, and there was a lot of engineering work that I didn't really mention here, but we had done a lot of engineering work to make it easier for the data scientists to understand the quality of the data, the distribution of the data, etc., to be able to do this quicker. So we built, like, for example, we had like a config file which decided how to interpret a certain variable and what to do with it, so that they could tweak it really, really quickly. So it's a JSON file. So for example, whether something should be considered as categorical, numerical, etc., and then train them accordingly. So we had automated that process. It looks at the data, it looks at the data type, uses a bunch of rules essentially to say, hey, if it looks like a number and has a large number of values, probably numeric, salary, right? It could be numbers but limited data size. It could be categorical, right? So it will suggest, and the user just had to do yes, no, yes, no, yes, no, manual classification. But we had built scripts for that. So that is what took longer, doing data cleanup and everything else. But the model training was really, really fast, because 25 gigs of data, like you could crunch it on a MacBook, like it's no big deal. But there's another thing as well, how you store your data, how do you classify it, etc., takes longer as well. So once you've optimized all of that, 105 seconds, but running all of those things, calculating the pre-features and everything takes a bit longer. Like the feature evaluation, right? Like that requires a service call, etc. Where do you get the data from, etc. Takes longer.
Your solution was to build one champion model, or
it's an ongoing process, right? So the solution was not just short term. So the short term solution was, can you save me money? So yes, build me a champion which is better. So statistics, the model before we stepped in had a 74 to 76% effectiveness, right? Which means 24 to 26% miss. And if you say, as an example, if you say they're losing,
how would those compare to the model?
the model we built was at between 89 to 92. So that's the uptick. And it took, the first version which came at 89 took us a month to develop, without any of the engineering, just like a data scientist sitting there just crunching through the data, coming up with a model. That's what got the funding. And it's like, oh, you can save this much amount of money. So we multiplied that by the total lost amount, let's say 10 million, right? So 26% of that is what you're losing. We saved X percent of it, right? 89 minus 76. You can do the math and you can figure out what amount of money you're going to save in the first year. We ended up selecting the model which was at 91 because I think it was 90-91 because the 92 and even got 94 once, we felt it was overfit. As in, like, it was made to work really well for the data set, but we felt like if it went to prod, it won't work as well. So we ran it in shadow. Ended up, like, the one which got promoted was around the 90s.
Very specific to this customer, or generic for other credit cards, or generic for other financial frauds like insurance?
I think it is, so the model is definitely accurate for North American credit card companies at the very least. Because if you think about it, like, think about it as a person who is committing fraud. Like, if I figure out I can steal money from you, what's the next thing I do? I find all of the people who do the same thing as you and I will probably steal money from them as well. Makes sense, right? Like, why will I take the effort of figuring out how to crack your system and just use it on you? And I'll try to find all the people I can steal money from and I'll use it in one shot. Best return of investment, right? So definitely that. Does it work on other products? Not exactly, because the data set is different. Yeah, so the 276 columns that we get is specific to credit cards. So when you take loans, the data set is completely different, which is why we have to build a different model. In fact, we experimented with completely different models based on time of year, because, like, there were theories we had. So one of the questions we were trying to answer is, how often does fraud change, such that if you don't plot like effectiveness of a model as like over the whole 25 years, if I take it in chunks, right? If I take it in smaller chunks and say I will, like how often do I have to change my model to get return of investment? Let's put it that way. Or how often do I have to retrain the model, right? Those are important metrics to calculate. So yeah, so all of those also sort of factored in, but I don't think it works for anything other than.
Final question. 25 years, is it not too longer because the latest product
Yes,
is
it is.
different from.
Absolutely, it is. So what we ended up doing, so we had tests on that as well, which is where like exploring your data is so important. So our theory was by using all 25 years you have a problem. So we tried the other way. We said, let's assume X number of years is all you need for any value of X. Tweak it, find out which one's true. And then we took a different theory, which was take the last X years and then weight it. And by what I mean by weighting is W-E-I-G-H-T-I-N-G, not W-A-I-T weight. So put a weight on it to check the more recent data is more important, and as you go further back, reduce it, right? And then we experimented with like biases of how you want to do it, how you want to weight it, etc., etc. Turns out weighting works better. What the weighting factor is dependent on the data you have, again specific to the client. But yes, weighting did work better. But this is a classic example of time series, right? And knowing your domain is super helpful. Like you said, how people stole money 25 years ago is probably different from what they do now. However, the thing we wanted to be careful of, the reason we didn't just like trim the data, theoretically let's say 6 years, right? 6 years is long enough. Who's going to repeat an attack? Guess what happens when people realize that? They're like, okay, let's figure out how people are stealing money 25 years ago. Let's take the same attack vector and apply it. Because I know for a fact you've not done this. Because the thing you've got to remember is while we have data scientists to reduce fraud, right, improve fraud detection, fraudsters have data scientists who are trying to steal money from you, right? So it's essentially an adversarial model. Both of you are trying to build models which are better than the other, except one of you has information and the other one's trying to guess, which is, if you think about it, very interesting because they are trying to test on a black box system to see what goes through. But their attempts for tests are good enough in itself for us to realize what is fraudulent application. So we can train on the attack vectors, on how they train their data, we can train on that as well. So it became like a very interesting conversation on what to consider, what not to, etc. So yeah, so you've got to take all of this into account. You can't cut off any data, you can't take all of the data, but what's the sweet spot in the middle where you can do everything?
This is a real-time system.
Okay.
So yeah, this is a real-time fraud detection system.
Yes, this is a real-time fraud detection system. Sorry, I forgot to mention one thing. The image that you saw at the end, like we built the system I mentioned at the very top. We built it such that it did application fraud in the beginning, but if you notice the system's got nothing to do with application fraud, right? So you could use it for transaction as well, which we talked about at the top, right? If the model is fast enough, which it was, because the model was responding in around, I think it was 25 milliseconds, we could tune it to make it better. But the point is, like the system works and works well. But if you notice that pipeline, the reason why I showcase that sort of value stream is because that has nothing to do with fraud at all, right? It has just something to do with how you should sort of maybe build your value stream. If you're building an application, you could probably, like those are the steps that you could probably sort of learn from, take as guidance and then sort of continue from there. Sorry, I don't think I answered your question. I just took a digression because I realized I didn't mention that.
It was just a part of it. So my question was going to be, if it was real time and you have to promote a new model, how do you coordinate? Do you have to tell the banks to like hold off transaction?
No, real time. So that's more of an answer of engineering practices. How do you deploy something while something's live, right? So we had zero downtime deployment throughout. The way we had achieved zero downtime deployment, and like this, because it's more focused towards machine learning, not as much about engineering, I skipped that. But what you do is on top of your service, you put a load balancer. Have the load balancer such that it is a zero downtime deployment switch. We were using blue green, which meant we started a new service up. Well, for shadow mode, actually, I take that back. For shadow mode, it's a hell of a lot easier because everything's in a queue. The moment you put the model on, the model, the queue, everything reads it from the queue like in a sort of greedy fashion. So it automatically load balances, etc. it's okay. So you will start processing it. But the moment you're trying to promote to prod, yes, that does come in where, how do you do it? Well, we deployed the other thing, and then when everything's up, health check passes, switch the load balancer and take the other one down. And all of that's obviously automated. None of this is being done manually. That's how we deploy.
Yeah, my question is like, you said like there are more
276 data points, yeah.
So was there any dependent data, that you have to rely on for it to make it more effective? An example is like, for example, an email could be an exposed email.
Yes.
Black market, like you
yes.
use that and buy it on your name, and that's potential
yes.
fraud as well. So does that take that into that variable also into the factor, like dependent data?
So that 276 was just what the bank had at the time, because that's historical data. They've always been, that's essentially every time you have an application, that's what they store, right? So transaction has a different data set, but similar in logic. But what you're talking about is essentially exactly dependent data or additional metadata I can add to make it better. Yes.
I mean, did you use any of those?
We did. So we used a fair bit. So a couple of them which I am allowed to talk about are the obvious ones. Like you mentioned, like exposed emails, exposed SSN, like those come in. And the location DB is the third example I already gave. So IP to location conversion is a service you can buy. There's a GeoDB. You can sort of buy a license to it. You can use it, pay per year, pay for a license. So those are the three, like one of them I mentioned, and two of them obvious that we also consume. But yes, for sure you have to supplant the data with more. And so the 50 odd features that we had.
That creates the variable, right? And
yes.
It has its own impact in terms of identifying more.
Yes.
Typical Gmail doesn't necessarily mean
yes.
It's not a fraud.
Yes, absolutely. Yes, but you can look at the whole email as well. But then that becomes a different side of data set. So what that ends up being in this example would be, it would be a Boolean value. Exposed email, yes, no, right? So once you calculate that, then you can train on top of that. Look at the correlation between that and fraud. If the correlation is high, then you probably want to use it, right? Like some stuff like that. So we did sit through that and analyze that, and that's part of the data discovery process.
So what is the plan to make the model more future ready, in the sense based on the model that is created is the past data?
Yes.
But considering the futuristic type of fraud that would happen,
yes.
Is there a way that the model will get trained automatically or become more intelligent as time goes? Is there any such?
Right. So the data pipeline part of it, the build pipeline part of it, I didn't spend as much time on. But essentially, actually, I don't want to pull up I can pull up the visual, but I don't think it's important. But the build process that we talked about, there was an automation behind it that I didn't sort of mention. So if you think about it, every time you get a request, actually, you know what? I take that back. I will go to the developer workflow. Let's go to developer workflow. Oh, that's not it. Yep, I think that's it. Okay. One of the champion model, which is next. Okay, yeah. So so this process, the thing that it doesn't talk about is application service. What it's been doing all along is every time it gets an application, it stores it into the database. So the thing that we trained on in the first place is that database, because this service has its own database. That's where we got the historical data for all of those years. And what we've set up in the build process is essentially taking the latest version of that, right, and then training on top of that. So while your model remains the same, one of the things which I think is beautiful, which a lot of app devs don't realize, is we're used to thinking of, like if you think about the relationship between code and artifact, it's essentially every time you change code and you compile it, you get a new artifact, right? The thing with models is you can change the code, you will get a new artifact. You can change the data, you will get a new artifact, right? So there's like 2 vector input to be able to change a version, right? It's not just one thing which changes the version of a model, right? So in our case, what we ended up doing was, let's say the code never changes. Let's say the data scientist says this is good enough, right? I want to continue running it. At the very least, the data is changing. So when the data changes, you want to retrain the model because newer data will make it better. It's not future proofing quite specifically, but like I think you had 2 parts to the question, right? One of them was how do you keep the model up to date? And that's essentially build that like full looping cycle. So when we built it once, when we did a commit, so as I said, code change triggers a build. The other one is data change builds it. Now, what data change means is every, let's say 3 seconds, there's a new person who applies. I can't keep rebuilding the model because it doesn't make sense. It's not cost effective, but also it's not going to make, one data point is not going to make a difference, right? So the other tweaking we had to do was based on analysis when we figured out how often does the data change enough for the model to, for you to warrant the model change was also important. The way we did that was we took an algorithm, trained it on a certain amount of data, purposely hid a certain amount of data, a couple of years worth, and then kept changing. And when was the score changing enough? How often was the model deteriorating? And once you knew that answer, you could say, let's say it is once every 6 months. It's not, but it happens to change. But let's say it's 6 months, right? So you would automate a build to say once every 6 months, just CI, right? Do a time trigger, once every 6 months, just build it. Just build it and deploy it. It will be better than the last one because statistics says so. Right? So that is how do you keep it updated is essentially CI. CI with triggers or CI with code change, one of the two. I mean, both are triggers, but time triggers versus code change. The other part is how do you keep it more future proof? I don't know if I have an answer to that. I mean, so what we did was we looked at the data and we tried to do the best we could. I don't even know how to start to answer how to make something future proof. Because like I think at least in my head, like models are usually like looking towards the past, looking at trends and trying to predict it. To be able to look towards the future would essentially say, I would come up with a feature that I think you might use, but the problem with that is once I train it on the past data, you might not have thought of that attack vector yet. So I might actually think of something, but you as an attacker have not thought of it yet. So therefore my model will fail validation on my side, right? Which means as soon as I throw it through the algorithm will, there's no correlation between this, screw it, don't want to use it. It will reject the feature automatically. So I don't think there's a way, unless there are ways to manually offset that as well when you're building a model. We avoided doing that.
Which could potentially create new ways of doing that, right? Which will create new futuristic ways.
Yes.
How different response. That could be one option, but I know that there could be multiple options.
One of the ways we thought of doing that was, and I'll be honest, we didn't end up doing this, but we thought of it because we had to have this conversation with our stakeholders. It's like, how do you keep this future ready? How do you predict the next thing before it happens? And the idea was essentially to build an adversarial model. So say, I will get another data scientist who does not know how I'm doing this. Get them to build a model, and its job is to attack. I'll give it the API in a sandbox environment, like make a non-prod environment and apply.
Antivirus companies kind of use that. Something that can be applied here.
Worth looking into.
Whether it's right now in production,
This thing? Yeah.
so like before working production, like, what is the test cases like you run?
So most of them rely on, so there's a list of test cases. The engineering side I won't talk as much about because I presume there are devs in the room and you're used to unit integration, all of that. So I'm going to skip all of that. So the test pyramid does exist there as well. On the machine learning side, one of them I mentioned, which was when the data scientist trained a model, for legal reasons, I have to make sure once the service gets built, that model gets put into a service and a jar gets built, a deployable jar, I want to make sure that the model is performing the same way because it makes sure that no one's tampered with it. Like neither the framework or no one's gone in and like messed with the class files, because that's an attack vector, right? Like, and we have to legally make sure that doesn't happen. And there's signatures and everything else to do protection. But that's one test, like black box, produce the same score. The other bits were more legal. So you generate test data, which you know there are laws for, redlining as an example, right? So you will generate test data because you know this is a redlining attack and you can't do this, right? So your model should not be influenced by those factors. And that's a bit like how you code that model to make sure that doesn't happen is different. But effectively, we want to force it to not have a correlation between, let's say, zip codes and fraud status. Because we know there is a relation, and the reason why that exists is because of socio-economic factors, and you want to exclude that. Right? So that becomes a test as well, because as I said, the slide after this, the governance team looks at these things. Right? So the sooner we test, the governance process, by the way, used to be 6 months. So and we didn't like that because it takes too long for it to get feedback, right? And I would like that to be quicker. So, and the way we did that was like, tell me what your checks are. I will prove to you already it's not doing that. I'll run a test because it's a lot quicker than what you do, right? So we run simulations, but like every other kind of testing, it's important to know how to simulate, what data to generate, and essentially we did like if you've done sort of a persona exercise sometimes when you build an application, what you do is you try to figure out what the personas for the application are. There'll be an admin user, there'll be a regular user, there'll be some other permission, right? So essentially roles will help you define how they use it, right? So we tried doing personas for people who are applying for credit cards. And obviously that's not a small list, it's a pretty large list. And there's variance amongst that as well. So we had like all of that defined out, and then we wrote tests on that to say, I know that this should or should not be caught as fraud. But that's research. That is research into data. That is research into the kind of people who apply for your credit cards. It takes a fair bit of effort, and it takes someone who understands the bank really well, and they have people who do. Right? So we paired with them, understood. We came up with some, they gave us some, built a whole data set. But that's how we tested. Because some of these are not even deterministic. So the thing with testing is, usually you want a deterministic answer. You want to say this is or isn't fraud, but the model actually gives you a number. So you can't assert that this application is going to give you 0.865 because it won't always give you 0.865. It will change over time. So how do you account for that? Well, you put a range, but how do you know that range is accurate? What range is good enough for it to be? Right? And those are more deeper conversations. There is no definitive answer. It was more based on like conversations with the legal team, with other data scientists who've been doing this for decades to say, what do you think is an appropriate answer?
Is there any case like you have a model in production and there's a reliable person, like you can give a credit card, but the model predict that person as a fraud person?
Happens all the time.
The application will actually reject that person, right?
Yeah.
So in that case, like how to overcome that situation?
Remember this slide? Everyone on this side? Yeah. So you're trying to reduce this. Remember I talked about this and the loss profitability formula right after this? We're trying to minimize the loss profitability. We will have people on both sides. It's a given. It's unfortunate, but it does happen, right? But the thing is, this image is great to understand, but it is also not factually accurate. This is like, we don't just take this line and then just say everything I'm going to reject. Remember I talked about strategies at the end? So what strategies is actually doing is it's cutting multiple lines to try to account for what you just said, right? Is to say, I know I will let people through, I know I will reject people, and I shouldn't. How do I prevent that? Let's say I do 10 lines, right? And I say, the last line, anyone on that side, I am sorry, you are a legitimate user, but there's these many legitimate users and these many fraudulent. So I'm willing to take that as a loss. Do the same thing here, right? At pretty much at this end. So what you'll see is, I know I have these many fraudulent users, but I have a lot more real users than fraudulent. So that's a good point to do a cut. Everyone in the middle is in that pendant state I talked about. So a human being is going to look at it. And how much time the human being is going to look at it, because you have thousands of applications every day, is based on how high your score is. The further you are to the right, the more time the person will investigate you. You are somewhere here, they'll probably call you up if you pick up the phone and confirm your name is right and like like 1 or 2 questions, they're like, dude, just give him the credit card, it's okay. It's fine, right? Someone who's here, probably like 6-point verification, send me this photograph. I don't even know what the whole process is, but it's very, very rigorous, right? And they're doing that because we think you're fraudulent, and if you're not, prove it. And if you want the credit card, do it. And people do it. People go through the process, right? So yeah, that's the way to minimize it, but there is no model way. There's no like magic answer to make this go down to 0. The thing is, anywhere in here where we know it's a wrong answer, we are trying to minimize by human intervention. So humans come in and help, like supplant and say, I know you said this is this way, but I am overriding. And the fun thing with that, is that over a period of time, when you collect data, you can actually do a training on top of that. So one of the things we took into input was for everyone in the middle, which is the majority of applications, what did the model think versus what did the human think? Right? And that's another thing you can train on. And whenever they don't agree with each other, and then take the actual answer, right? Like, so what the model thought, what the human thought, and what was the actual answer.
So you will get that data point also.
Yes, we had that data point as well because we had like a ton of data, right? So that is another feature you can develop is to actually prove how accurate your people are. And if they're not, then the answer is then you can analyze why they aren't, right? Which is there's additional data set. So for legal reasons, every time you accept or reject someone through this verification call, there's a data set which is generated separately, which tells you why you came to that decision, right? So then you can run analysis on top of that. Every time you know you were wrong, you can then maybe run a clustering on top of that. We didn't end up doing this. We suggested this idea, data scientists picked it up, one which belonged to the organization. So they ran, like we said, do a clustering, figure out what the trends are, like figure out why you are getting it wrong. Either way, right? You're rejecting good people or you're letting bad people through, right? Like why is that happening? And you do a clustering on top of that. I don't know what the answer to that is. I'm sure they figured it out, but we essentially set that up as a feedback process. So now what you can do is, because of that, you can set up your business process. The strategies that you had or the questions that you had, you can make them better to make them more effective. So you can learn from your mistakes, which is again a thing that they weren't doing. Sounds so obvious, but when you run a business this large, which is taking like a ton of applications every day, it's just taken as operational cost to say, I'm going to let this money on the table, it's okay. Because it's too hard to optimize. But when you bring technology into the loop and you give smarter reporting, essentially it's reporting, right? You're saying, here's the reason why you didn't catch them. Here's what I think has happened. Here's the simulation of how you can make it better. Doing that as an A/B experiment is a culture we started in the org. Because we started with models, we then said you can do it with this as well. So they've then taken it up and started doing it. But these are some of the fun things you can start doing when you have information. Like we didn't know we would do this, but came out as a byproduct.
What that increased subjectivity, because when you are dealing with data with so much amount and you are doing cutting it, and suddenly you are also feeding the same engine with the subjectivity from the human nature.
So yeah.
Won't that decrease the model value?
It could, right? So we didn't end up using, I don't think we ended up using the data, but we had it as a data point. The model ended up rejecting it. So model also like evaluates the weights, right? Like when you do a random forest, you can throw at it a bunch of things that you think are important. Then it'll come back and say, no, these are important, these aren't important, right? Like zip code, for example, we experimented and we looked at the result correlation, it was very high. For some of the other things, it wasn't. But then the data point was used for other things. It was used to make your process better, which is again valuable in itself. So you spend that money and that time to come up with a feature which is useful, just not to make your model better. But overall, if you think about it, the program's responsibility was to reduce the cost, right? Reduce the cost for loss due to fraud, which you have. So win nonetheless, right?
To realize the benefit?
The building the model was pretty quick. We built, as I said, like at 89 it was like in a month. Then we had to do 4 months worth of engineering work to do the other stuff we talked about, the automated build, the testing and everything else. We could probably spend another 6 to 8 months making the product even better. It ended up we had developers on the team who could do it as well. So we started pairing and transitioning after I think 6 or 8 months. But in 6 months the product was like there, like in terms of like model being there. Now the models, did they improve over time? Yes, because we were doing two things really, right? Like we were doing the building and engineering framework, which allowed you to do this repeatedly, very, very quickly. That was one of the goals. Not a business goal, but like an IT goal, like a tech goal. Tech wanted to be better at this. And then the business goal was to make the model more effective, which technically you had it in a month. You just had to put it through governance. And putting it through governance takes a couple of months, etc. We said we'll automate all of that for you. Again, engineering work, but which ends up helping you in the long run. So realizing the value in terms of reducing fraud cost, the thing you have to realize with fraud is, and here's the fun thing I didn't say earlier, it takes 6 months for 80% of application fraud to realize. Like absorb that for a second. You apply for a credit card, you don't start stealing money day one. I mean, you could, but most people don't. Like the novices do. The ones who are smart will spend a lot of time. They will pay their bills. Like, which just baffled me, right? Like the first moment I was like, why? You're here to steal money. Why are you giving money away? Because by giving money away, your credit limit actually goes up. So when you hit them hard. So I asked them like, how long do you have to wait before you're confident that someone has, like, that someone's legit, like they won't commit fraud? right? Which is an answer of saying do a probability distribution between the amount of time, the time duration before you realize they switch from fraud to not fraud. And they're like, if you want to consider, let's say 99 percentile, right? 99% of all applications which are fraud, how long do you have to wait for that? The answer was close to 3 years. To get 99%, it took 3 years, right? 35, 36 months, which is just staggering. I was like, and what about the last 1%? It's like, we're never sure. Because we have outliers. We have outliers, people who paid their bills for 7 years before they've stolen money from us. I was like, what kind of long play is that? Or is that just a person just being like, I forgot this is not my credit card, I accidentally kept paying it. I don't know, right? But it's interesting. But what that means is, once you predict something's fraud, it will be 6 months before you're about 80%, 60, 80% accurate, right? Like you're 60 to 80% confident that someone was fraud versus not. But you're not sure. 3 years later, you'll be almost certainly sure. So the truest sense of the answer is never. You'll never be sure whether if you predicted someone as fraud and it's marked as fraud, yes. By the way, it goes from fraud to not fraud as well. So something might be marked as fraud, which will later be overturned. Because what happens is the person realizes, picks up the phone, is like, what do you mean I'm not fraudulent? This is my credit card. And then they go through the verification. So it goes back. So it's a very complicated domain, unfortunately. It's a business process. Exactly. It's got nothing to do with us, but it's a business process. But it does have an effect on us, right? Like as people who are trying to build a system to make this better, you are never 100% sure whether your answer is right? But I guess 99% is pretty darn good. But that's also 3 years later. So you're 70 to 80% sure that you got it right in 6 months. But 6 months is also a pretty long amount of time. And when you start considering all of these things, you start realizing why they were like, I'll change a model in 3 years. Right? So they used to deploy a model once every 3 years. The vendor would be like, I'll drag my feet. Not drag my feet. They had tons of things to do, I'm sure. It just took them a long time before they deployed because of the engineering processes they had. So we just made it faster. It made it better for us to deploy. We didn't get full feedback, but the model got trained, right? Which has its own implications if you think about it, because you're always training on slightly off data. You can't really trust the answer of the model for anything which is less than 6 months. You might as well just drop it during training, right? Because you're not sure. And this is where, like, if we should do a whole separate conversation on how to prep data because it's super interesting. But once you start if you don't ask this question, you would have trained in the first 6 months as well. You'll be like, first 6 months, nothing's fraud. Everything's great. It's not. The quality of the data is, over a period of time, you get more and more certain about the quality of data. So technically speaking, like in the first 6 months, we just dropped it. It's not even worth it. Because you are not going to get reliable trends out of it. Because it will go back and forth. Something might be marked as not fraud, which will be, everything starts as not fraud, but it will become fraud. It might come back as well, multiple times. So just don't. It's not worth it.
Okay, guys, we'll take these questions offline. I think Karun will be around. We'll also be around.
Yeah, this is a small announcement before we use Profitability. Like if any one of you want to speak on anything interesting in the DevDay meetups, like please write to us at DevDay. Like let me
yeah, we'd like to get more, people from the community to actually come and speak rather than people in Sahaj account. It may not be machine learning or AI, may not be restricted to that. We've even done DevDays which are purely focused on things like front end. So yeah, please feel free, reach out to us, email, meetup, Twitter, email, whatever.
If there's a topic that you want to speak about, please let us know. If there is a topic you would like to hear more about or you have interest in, please let us know, and if we can find a speaker, we will try to accommodate that as well. Right? Works both ways, but yeah, this is really meant to be a community-driven thing. It's not just like a bunch of us just sharing our experience. It's a two-way conversation, which is why this conversation is so important. But we'd like to sort of take that forward and have some of you share your success stories or failure stories, because that's super important to learn from as well. You can put it on topics, okay? So yeah, please do come, drop an email, talk to any of us, and we'd love to have you on stage here sharing your experiences in the future. Because that's how we all grow together.
Okay, guys.
Okay? Yes. What was the default? What do you mean default fraud rating? Sorry, I don't. Default score? Go for it. what was the percentage of fraud for? Oh, I know the answer to the question. I'm thinking whether I'm allowed to say it or not. Just give me a second. It was pretty low. Let's flip this around. Let's do this as an audience participation. What do you think is the average application fraud rate in North America? Let's do ranges, right? Let's do 20% blocks, 0 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 100, right? Show of hands, 0 to 20. Oh, you want smaller buckets? Okay, after, if you have majority of votes in one bucket, we will break it down further. 0 to 20, about probably around 40, 50% of you, right? The next bucket, 20 to 40. Okay. Anyone think it's above 50? Unlikely, right? Okay, okay. So the ones who are, by the way, out of these two, 0 to 20 is correct. Do you want to sub it into 5, right? 0 to 5, 5 to 10, so on and so forth. Where do you think it is? For the ones who voted 0 to 20. 0 to 5? 5 to 10? Anyone above 10? No? Okay. The answers between the 5 to 10 range, somewhere in the middle. So yeah, you guys were pretty close. There are certain times of the year. So the answer actually is it depends. It depends on what time sample you take, because it does vary by time of year. So there is a time of year where it goes up to 15% approximately. Exactly, right? So anyone who knows the North American market knows. By the way, there's food here. Please feel free to help yourself because I'm feeling hungry. I'm probably going to pick one up. Yes. And feel free to ask me any other questions. So
anyway, it's an imbalanced data set, right? So what technique do you apply for that?
What do you mean by imbalanced data set?
The number of fraud